Hello everyone, this is part 4 of section 15.2, and hopefully we'll be able to get through the rest of this unit at this point. Last time we left off in the middle of this problem, we're identifying how to set up the integrals for the three regions labeled Roman numerals 1, 2, and 3. And just to recap, Roman numeral 1, vertical strips, because we're fixing x. We're going in the x from 0 to 2 because that's region 1, and 0 to the function, and the function is positive square root of 4 minus x squared. So for the region labeled as Roman numeral 2, dy dx again, because we're fixing x. Notice that this little portion here would be our vertical strips. And now we're going from, in the x direction, from -2 to 0. So that's the only thing that really changed, because the y direction 0 to the function, which is still the top half, square root of 4 minus x squared. So then for the third region, now we're on the bottom half of the function. Take any vertical strip that you like, but realize we're going all the way across. So when we set up the double integral, again, dy dx, because x is fixed, x is the outer. So that's going to range from -2 all the way to 2. And then the function is going to go from, the lower limit is this portion of the graph, which note is the negative square root of 4 minus x squared, and we're going up to the x-axis, which is 0. Okay, so that's doing it for the type 1. For type 2, where y is fixed, okay, let's redraw the region, and also note that we need x in terms of y. So if you start with either the original circle or the modified version, let's start with the original circle. X squared plus y squared is 4. And now we solve for x in terms of y. So x squared is 4 minus y squared, and x would be plus or minus the square root of 4 minus y squared. So now when we draw our circle, again keep in mind the radius is 2. The left half is going to be the negative, and the right half, so x equals the positive square root of 4 minus y squared, is the right half. GHT half, and the left half is going to be x equals negative square root of 4 minus y squared. So that's the left half. Okay, so now we're ready to set up the integrals for what we're labeling as Roman numeral 1. Do the same ones, 2, and then this one, again, we label as 3. For 1, now we're taking horizontal strips. Okay, so we're going from, right, and we're fixing y. So it's going to be in the order of dx dy, because y is now the outer. We're going from, and remember these are all 2's, to -2 over here negative 2 here, radius is 2. Okay, we're going from, in the y direction, we're moving from 0 to the function. So, I'm sorry, that's in the x direction. 0 to the function. Normally I took care of the y's first. If you want to take care of the y's first, you're going from 0 to 2. That's the outer limits. And then 0 to the function, which is the positive version of 4 minus y squared for that region. And then for region 2, we'd have the double integral from, okay, now we're taking horizontal strips in this direction. And so we have from the left side of the function would be our, well, let's do the y's first, because, okay, this is going to be dx dy. Y's are still going to go from 0 to 2, but now we have the left half of the function, which is the negative square root of 4 minus y squared to the y-axis, which is 0. Okay, and then finally for number 3, for region, what we're calling region 3, double integral dx dy. Y is going to now range, so now taking horizontal strips like this, and y is going to range from lower negative 2 to upper of 0. And so that'll give us, cover all those little horizontal strips, that gives us that region. But now notice how x ranges from the left half of the function to the right half. So negative square root of 4 minus y squared to the right half, positive square root of 4 minus y squared. Oops, I'm sorry, I kind of cut those last two off. I apologize for that. So, give you a second to catch up. Sometimes we have to complete the square to sketch the region. Consider all of these are just numerical values, but the upper limit here is y is the square root of x minus x squared. So that's the situation where it is a circle, but we have to complete the square on it. So notice how it's similar to the circle that we generated, or that we were talking about in the last example. So completing the square, here I'll show you what we need to do. So first square both sides. Then let's get everything to one side. So we'll square both sides, we get y squared equals x minus x squared. Everything to the left, let's say x squared plus x plus y squared is 0. We'll complete the square on the x squared plus x plus something, and then plus y squared equals 0 plus something. What completes the square is you take half the coefficient of the linear term, so half of 1 is 1/2, square it, you get a quarter. So if I add a quarter there, I have to add a quarter here. This is now a perfect square trinomial, which is expressible as a binomial squared. First term x, second term, recall whatever half the linear term was before we squared it, sign included, so in this case plus 1/2. And, well, I'm sorry, that's minus, so I made a careless mistake there. This should have been a minus, that would have been a minus, and this would have been a minus. Okay, so that's a minus, and that's a minus. Okay, but nothing else changes because squaring a negative is a positive. Alright, and then we've got the plus y squared equaling 1/4. So therefore that's a circle, and the center is at the point 1/2 and 0, and the radius, well, r squared is a quarter, so the radius is 1/2. So basically we have, in terms of a sketch, I've got a circle now with the center at 1/2, 0. Must be 1/2. Make that a little bit more clear. Okay, that's the point 1/2, 0, and its radius is 1/2, so I guess over to 1 and 0 are going to be the endpoints. Go up to 1/2. It's really the top half of a circle, right? Because it's the positive square root, so it's the top half. And the bottom half would be the negative square root. Okay, last question. Returning to average value concept. And I chose the question actually that's in your homework. I don't mean to hurt your academic integrity, but when I looked at these, I thought, oh my gosh, that's pulling out some tricks. So instead of you really struggling with your homework, try the homework problem, then come back to this video if you like. But this hopefully will clear things up with this particular homework problem. Remember, the average value is really the volume over the area, okay? And they tell us that we want to find the average value of this function over the region, triangular region with these vertices. So let's make a sketch of that region. So it looks like just label some 1s here, and we've got 0, 0 is a point, 1, 1 is a point, and 0, 1 is a point. So looks like this would be the region, triangular region we're looking for. And so the average value, let's do the top. Remember, it's easiest to do these in parts. Let's do the top part first. So the integral of the region of this function with respect to the area will be the double integral of 1 over 1 plus x squared. And I'm going to do this with vertical strips, so fixing x. So with respect to y first, then with respect to x. So x is the outer. Okay, so if x is the outer, we're going from 0 to 1, okay, to get the entire, all these little vertical strips added up to give us that triangle. So the outer I'll label 0 to 1. And then we're going from this function, the line, to y equaling 1. So upper is 1, and this line is the line y equaling x. We know that, of course, because the slope is 1, because we're only going from 1 to 1. So don't need anything fancy to figure that out. So the lower limit is going to be x. Okay, so we're integrating with respect to y first, and so therefore we get the integral from 0 to 1 of, this is just a constant, times the integral dy would be y, because 1 dy, and so that's y, so let's say y over 1 plus x squared, evaluated as y goes from x to 1. And then that's with respect to x. Okay, so then fundamental theorem of calculus, integral 0 to 1, upper limit, some brackets here, 1 over 1 plus x squared, minus lower limit x over 1 plus x squared. So now we just need to evaluate those integrals. And this is why I chose to do this problem for you. I know some of you are certainly proficient enough and recall, but one of the things that I thought you haven't seen in a while is this first integral. Second integral, you should know that one without a problem. That's just going to be a u substitution to fit the form of du over u. But then this first one, you have to pull out the formula for du over a squared plus u squared, which results in 1 over a inverse tangent of u over a. But this is a case where a is 1. I mean, if you wanted to show it formally, a squared is 1, u squared is x squared, so a is 1 and u is x. Your du would just be 1 dx. Kind of silly to make a u substitution on that. And that's something, as I told you in Calculus 2, you might even want to remember the basic integral for 1 over 1 plus x squared. Since a is 1 and u is x, that's just the inverse tangent of x. And then here, you'll need a u substitution if you want. Or if you could do this mentally. And by mentally, I mean all that's happening here if you make this u substitution is you get a modification by 1/2. Because the denominator is your u, and the x dx that's in the numerator makes up 1/2 du. So I'll just recopy this as it is for now, because again, no u substitution really necessary. If you want a u substitution here, minus 1/2, I'll do integral a to b du over u. Recopy. I won't do all the integrations at once. Oops. Could have integrated them. So doing the integrations now. We have inverse tangent of x evaluated from 0 to 1 minus 1/2 natural log absolute value of u. Evaluated from a to b. So that's inverse tangent from 0 to 1 again. I'll just recopy that. Now I'll put back my u. Was 1 plus x squared. So 1/2 natural log absolute value of that evaluated. Now I could say I'm going from 0 to 1. Okay, so then at that point, inverse tangent of 1 minus inverse tangent of 0, and then minus 1/2. Use brackets, parentheses here, natural log upper 1 plus 1 squared minus lower natural log 1 plus 0 squared. Okay, inverse tangent of 1, if you have to, use your calculator, or you can do, if you have it in terms of degrees, you're going to get 45 degrees, or you can make up the triangle and go through the formal way to evaluate the inverse tangent of 1. That's 45 degrees, or if, you might want to do it that way in terms of degrees and then change it to radians. Inverse tangent of 0, 0 degrees or radians. Minus 1/2, this would be natural log of the absolute value of 2 is 2. And we have minus natural log of 1. But the natural log of 1, we know, of course, is 0. So we get 45 degrees, but we have to put that in radians, pi over 4. And then minus 1/2 natural log of 2. And then that's just the numerator for the denominator of our formula. That's the area. But there's really no need to do any calculus with regards to the area, because it's just a triangle. So you could say that the double integral of the area, so our area, geometrically is just base times 1/2 base times height. No need for anything fancy in terms of integrations. The base is this one and the height is this one. It's just a right triangle. Here's your right angle if you wish. And so 1/2 times 1 times 1, or 1/2. So therefore the average value is, the numerator is the volume, pi over 4 minus 1/2 natural log 2. Denominator is the area, 1/2. If you invert and multiply and distribute the two, if you want to show it this way, 2 times, literally show pi over 4 minus 1/2 natural log of 2, and then distribute your 2, get pi over 2 minus natural log of 2. Okay, so I thought I'd help you out with your homework there on that question, because of little tricks with the inverse tangent and such. So if I ever plan on giving you something like that, I'll warn you about it. Alright, so that ends 15.2, and we'll see you when you get back for 15.3.